Hello everyone, myself Sivaramakrishna, faculty in Electronics and Communication Engineering. Welcome to the lecture series on IC applications. Today we will continue the discussion on analysis of differential amplifier. So if you remember, last class we have seen analysis of differential amplifier in the context of differential mode. So that means especially for DC analysis we made. Any amplifier can be made for the analysis. The analysis can be made in the context of DC as well as AC. So in the last class we have done with DC analysis of differential amplifier. So that is what are the steps to be considered for DC analysis? The first and foremost step is suppress all the AC components, keeping only DC components as active. Suppress all the AC components. So that means redraw the circuit by suppressing all the AC components. This is what the equivalent circuit we consider for the DC analysis. So if you observe, there is no AC component, even there is no AC input signal, right? So with that circuit we perform the analysis. And what is the main objective of DC analysis here? It is to determine the Q point. The main objective is to determine the Q point. So that is we find the expression for VCEQ and ICQ. We determine the expression for VCEQ and ICQ. So this is what the expression for ICQ and VCEQ. So this is the main objective of the DC analysis. So strictly speaking, DC analysis is to fix the operating point of the amplifier. So same way what we did for basic amplifier. Basic amplifier in the sense a common emitter or common base or any transistorized amplifier, we need to fix the Q point. We need to fix the Q point in the characteristics, right? Especially on the output characteristics of the transistor, one can fix the Q point. So as we said, it is strictly at the center of the characteristics. So it is not at the saturation point or it is not at the cutoff region. So since we want to operate the circuit as an amplifier, we need to fix the Q point exactly at the center of the load line. So using this DC analysis, we are able to find the expression for the Q point, that is VCEQ and ICQ. Of course, these two expressions are represented in terms of the biasing voltages. So in the expression, if you observe, there is VEE as well as VCC. Both are nothing but the biasing voltages. So VEE is the biasing voltage provided to the emitter terminals of the two transistors, and VCC is the biasing voltage provided to the collector terminals of the two transistors. And another important point to remember, VEE is a negative biasing. VEE here it is a negative bias, and VCC is positive bias here. VCC is going to be the positive bias. That is what applied to the transistors, both the transistors. So up to this we have done in the last class. Now we are going to perform the AC analysis. So do always remember, the amplifier analysis is carried out in DC mode as well as in the AC mode. So that is, the amplifier analysis means DC analysis as well as the AC analysis. In the DC analysis, we are going to fix the Q point of the amplifier, that is operating point of the amplifier. In the AC analysis, what we can determine, what are the objectives of this AC analysis. So what we are going to determine here, let us look at this here. So here in the AC analysis, we are going to calculate the differential gain AD as well as the expression for common mode gain AC. If you remember the basic amplifier, that is a transistorized basic amplifier. The AC analysis is carried out for determining gain. What kinds of gain we are going to determine there? It is going to be the voltage gain AV and current gain AI. These two gains are obtained under AC analysis, are the two important gain parameters. So that will gain is one of the important characteristics of any amplifier. If you design any amplifier or you want to design any amplifier, the first question you need to ask here is for how much gain we need to design the circuit. So if you design any amplifier circuit, what is the amount of gain that it can produce? That is going to be the question to be asked in any design question of an amplifier circuit. Okay, similarly in differential amplifier, we are going to determine two gain expressions. So one is going to be the differential gain AD and another one is the common mode gain AC. Of course, we are also going to determine input resistance Ri and output resistance Ri. So these are two usual general parameters to be measured while analyzing any amplifier. So altogether, so the AC analysis is meant for determining the expression for gain and impedance. We are going to determine the expression for gain as well as the impedance. Gain means we are going to determine the differential gain AD and common mode gain AC, and input impedance means this is nothing but the input resistance Ri and output resistance R0 we are going to determine here under AC analysis. So now, as usual, what is the first step? What is the first step in the analysis to perform AC analysis here for a given differential amplifier? So as usual, all the DC components to be suppressed. So there will not be any DC component. What are the DC components in the circuit? If you remember, there are two DC biasing voltages. What are they? One is the VCC and another one is the VEE. These two voltage components are there primarily. They are going to play a DC role there. And what are the AC components here? We have two AC components in the differential amplifier. What are they? AC components are nothing but the two input voltages. So what are they? We can say V1 and V2. V1 and V2 are the two input voltages, are AC, are supposed to be AC. V1 and V2 are nothing but the two AC input voltages. So V1 is the input voltage applied to the first transistor and V2 is the input voltage applied to the second transistor, are in AC nature. They are in AC nature. So that is what we need to highlight while performing the AC analysis. All the DC components. So the predominant DC components present in the circuit are nothing but the biasing voltages. What are they? VCC and VEE. These two components are not to be considered in under AC analysis. We are not going to consider these two components or parameters. We will the circuit, the entire analysis is completely focused on determining the common mode gain as well as a differential gain by considering the two AC input signals. What are they? V1 and V2. V1 and V2 are the two input voltages. So let the two AC input signals, these two are the AC input signals, let it be equal in magnitude. See, we consider differential amplifier. How we design the differential amplifier? By considering two symmetrical transistors. They are very identical. They are ideal in nature. See, similar kinds of semiconductor means it is going to be the germanium. If it is a germanium, both are going to be the germanium transistors. Silicon means both are going to be the silicon transistors. So we consider two identical transistors in the design of the differential amplifiers. And we said there are two AC inputs. What are they? V1 and V2. Again, in terms of the magnitude, what is meant by the AC signal? AC signal is going to have certain magnitude. This is what AC signal is going to have certain magnitude. So this is what the peak to peak voltage. So let it be, this is going to be the magnitude. Let the two inputs are going to have the similar magnitudes, V1 and V2. We can say that V1 is equal to V2. No problem. even if you say even in that manner also. So two AC signals be equal in magnitude, and look at this one. There is 180-degree phase shift. So there is 180-degree phase shift. What is by the 180-degree phase shift here? The starting point of the two input signals is not same. There is a delay of 180 degrees. 180-degree phase shift means that is what the delay we introduce between the two input signals. There is a delay of 180-degree phase shift. However, they are going to possess the equal magnitude. Magnitudes of both input signals are going to be the same. The magnitudes of each input voltage V, that is Vs1 and Vs2 primarily, because these two are considered as the source voltages, source input voltages, be Vs by 2. Both source voltages which are applied to the transistors is said to be Vs by 2. The two AC emitters, so we have two emitters, right, because of the two transistors. The two emitter currents say that IE1 and IE2 are equal in magnitude. Again, there is 180-degree out of phase shift. So you try to understand, we consider AC, we are going to describe the nature of the AC signals. We are going to describe the nature of the AC signals that are applied or provided to the differential amplifier. So one thing you need to remember, that is in terms of the magnitude, they are same. In terms of the phase, there is 180-degree phase shift between the two. So this 180-degree phase shift is carried out throughout the analysis. Even if you say Vs1, Vs2 or V1, V2, and now it is going to be the IE1 and IE2, that is even if you consider the emitter currents of both the transistors, in terms of the magnitude they are equal, but in terms of the phase shift, there is 180-degree phase shift. Hence they cancel each other. Anyway, that is the secondary thing. Now for the AC purpose, emitter terminal can be grounded. So that's what we have seen. We can find the same thing in the very beginning of the circuit. So what is the construction here? Both the emitter terminals are tied together through a resistor. That's what we said. So another thing, how to perform the AC analysis? That is a big question. How to perform the AC analysis? So whatever we said are nothing but the preliminaries. Before we perform the analysis, before we begin the analysis, how to perform this analysis? What with what kind of parameters to be considered? Based on what parameters we are going to design or analyze the AC? We are going to perform the AC analysis of the amplifier. That's what we said. So what we said, in terms of the magnitude they are equal, but in terms of the phase shift there is a delay. There is a delay, that is 180-degree out of phase, we said. Now the question, big question, how to perform AC analysis? How to perform AC analysis? So here is going to be the hybrid parameter model. So how to perform this one? That is hybrid parameter model. We are going to consider hybrid pi model, not hybrid parameter model. Not this, it is not going with hybrid pi model. That is different. Hybrid pi model is different, used for high frequency analysis. And here it is going to be the hybrid parameter model. So this is what the circuit we consider for AC analysis. That is a AC equivalent circuit. AC equivalent circuit for differential operation. So what is the circuit now? Here we said Vs1 and Vs2. Vs1 and Vs2. So what is their magnitude here? We said that this is going to be the Vs by 2, and there is a source resistance. Of course, this is the nature of the first transistor, whatever we consider here. And here is your output of the first transistor, right? And look at this DC bias. What is the nature of the DC bias? It is ground. So what is the condition we consider for AC analysis? There will be no more DC component. That means there will not be any DC component present in the circuit. The circuit completely described in terms of the AC components only. So that's why the DC biasing is said to be ground. It is grounded, and anyway here we are going to get the output voltage. That is, the output voltage is said to be the V0 here, right? For the same thing, we are going to draw the hybrid parameter model. So the amplifier analysis is carried out by its small signal equivalent circuit. What is a small signal equivalent circuit? Is nothing but the hybrid parameter model. So if you remember this hybrid parameter, this is very useful for you. Okay, this is just an extension to that of your basic amplifier, whatever we did in the previous course actually. So this is the hybrid parameter model. You know about the HIE, HFE, IB, and what is the nature of the two transistors. You can see that anyway, emitter terminal is grounded because we are operating the transistor in common emitter mode. We are operating the transistor in CE mode. Whatever the input, AC input, that is applied to the base of the transistor, and output is measured across the collector terminals of the transistor, right? Across RC we are going to measure the output here, right? This is the equivalent circuit of the transistor, and this is its corresponding hybrid parameter circuit model. Based on this, we are going to determine the common mode gain as well as the differential mode gain. Right, now let us continue with the analysis. So we represent the equivalent circuit and its corresponding hybrid parameter model circuit. So as usual, what we can do now, we need to apply KVL. This is the first step here. Apply KVL to the input section. KVL to the input section of the transistor. So what is the KVL here? I mean, here you can apply. This is your input section and this is your output section, right? So what is meant by the hybrid parameter model? The entire transistor is replaced by hybrid parameter model. So this is your input section and this is your output section, right? So here the entire transistor is replaced by hybrid parameter model. So here this is going to be the input section. This is your input section. This is the input section of the transistor and this is the output section of the transistor. So as a first step, what we are going to do, apply KVL. So what we are going to do, apply KVL across the input terminals of the transistor. So what are the components present in the input terminal? We can say RS is there and input current is represented by IB, and there is input resistor, that is HIE is there. So we will see the expression that it becomes Vs by 2 is equal to. So what we are going to say, Vs by 2 is equal to. So there is only one source. If you observe in the circuit, applying KVL to the input section of the hybrid parameter model. So here the only source is Vs by 2. This is going to be the source. This is the only source here, right? And Vs by 2 is equal to, what are the components are there? How many resistive components are there? If you observe here, one is RS is there, another one is HIE. That is, whatever the applied voltage, it can be divided among the two resistors. What are the two resistors? RS as well as HIE. So what is the current here? There is only one current, that is nothing but IB, where IB is nothing but the input current. IB is nothing but the input current, right? Now let us see the expression. Vs by 2 is equals to IB into RS plus IB into HIE. Is there any other parameter present in the circuit? If you observe, see here, this is only the input section. I am asking you to consider only the input section. This is the only input section. Applying KVL to the input section only. We have only one source voltage, that is AC in nature, which is Vs by 2. How it is divided? It is divided among the two resistors, that is RS as well as HIE. The current flowing here is nothing but the IB, that is. So if you rearrange this expression, what we can get here? So bring all these components into the other side. So it will become Vs by 2 minus IB HIE minus IB RS is equal to 0. We are going to obtain. Now what we can take common here? You can take input current IB as common. So what we can write here? So we said we have Vs by 2 minus IB RS minus IB HIE, right? So take IB as common. So what we will get here? Taking IB as common, we left with RS plus HIE. We are going to have RS plus HIE. This is what we are going to have. So further you can rearrange it. So what we can get here, if you take this to other side, what we will have? Vs by 2 is equal to IB into Rs plus HI. The same expression, whatever defined here, right? And now, what is required here actually? Let us obtain the expression for IB. What is the expression for IB now? If you take IB, if you measure IB is equals to Vs by 2 into Rs plus HI. So this can be treated as another equation here. So do remember, by applying KVL to the input section, what we are going to determine? We are going to determine the expression for input current IB. We are going to obtain the input current IB by applying KVL to the input section. Similarly, we are going to apply KVL to the output loop. So what is your output loop in the circuit? So this is your output loop. This is your output loop, right? So here we are going to apply the KVL. In the output loop, what will be the expression? There is output voltage V0. There is output voltage V0 is equal to, how will you represent that output voltage? If you see here, see this is your output voltage we set. It is measured across RC, that is drop across RC, right? So what is that expression? It will become minus HFE into IB RC. This minus is because of the nature of the direction. Okay, so we will define it as V0 is equals to minus HFE into IB into RC, and we have determined the expression for IB already. What is the expression for IB? IB is equals to Vs by 2 into Rs plus HI. This is already determined. So substitute the value for IB, substitute the expression of IB here. So what is going to happen now? V0 is equals to, what is V0 now? It will become minus HFE RC into Vs by 2 into Rs plus HI. This is going to be the output voltage V0. This is going to be the output voltage expression for V0, right? Now what we are going to determine? Gain. Can you remember the expression for gain? So what is meant by the gain here? Gain is nothing but the ratio. Gain is the ratio between output to the input. What is your output here? It is your voltage. So output is going to be the output voltage V0 by input voltage. What is input voltage? Vs. Vs is nothing but the input voltage or source voltage, whatever it is. This is going to be the voltage gain AV, right? So by performing, from the equations 1, 2 and 3, considering all the three, you can find the expression for gain. So how can you find the expression for gain? Look at the equation 3. In equation 3, it is aiming for determining the output voltage V0. It is aimed to determine the expression for V0. V0 is equals to, it is expressed in terms of Vs. So do the cross multiplication. What we will get here? V0 by Vs. We can find V0 by Vs. That is, so just perform the cross multiplication. We can get V0 by Vs is equals to, so what is the leftover parameter? What are the leftover parameters in the equation? We have HFE into RC by 2 into Rs plus HI, right? So 2, this is nothing but HI here. So this is your V0 by Vs. What we can say V0 by Vs? Nothing but the gain. Which gain? Voltage gain. See here, it is a ratio between the output voltage V0 to the input source voltage. Input voltage, that is Vs. So it is given by minus HFE into RC by 2 into Rs plus HI. So keep a note of this expression, right? So that is your gain. That is the gain which we have determined. And now, since it is not an amplifier, it is not a basic amplifier. It is not a basic amplifier. If you consider a basic amplifier, there is only one transistor. This is the differential amplifier. This is your differential amplifier. So here, both the transistors are going to have some kind of gain, are going to carry some gain values, right? If you have a transistor, will carry some gain. Now the interesting factor here is, what is the differential gain and what is the common mode gain? Now see here, the negative sign in the expression indicate there is a phase difference. That's what we said in the very beginning. There is a phase difference. See, in any circuit expression, if you note, if you find minus sign, negative sign, that indicates the LHS parameter and RHS parameters are in phase shift. Generally, it is going to be the minus. That is, minus represents 180-degree phase shift. So that is what here. If you consider V0 and Vs here, so what will you observe here? There is a minus. There is a minus. Nothing but there is a 180-degree phase shift between the output voltage V0 and input voltage Vs. There is a phase shift of 180 degrees between the output voltage V0 and input voltage Vs. So that is to be noted. In any expression, if you find there is a negative relation between LHS and RHS parameters, this is what you need to consider. Now see here, we are going to define the parameter called Vd. What is Vd here? Difference voltage. So what we said, Vd is equals to, what is Vd here? Vd is equals to V1 minus V2. So what is V1 here? V1 is the input applied to the first transistor and V2 is the input applied to the second transistor. So in differential amplifier, the name itself indicates it is a difference. It is a difference. So what is the expected outcome of this circuit here? The output is going to be the difference among the two amplifier circuits. So you can say that Vd is equal to V1 minus V2. So where V1 is the input of the first transistor and V2 is the input of the second transistor. So what we said the value for V1, Vn is defined both V1 and V2, both magnitudes. The magnitudes of both V1 and V2 are said to be equal. What are they? Vs by 2 minus V2 is also Vs by 2, but there is a 180-degree phase shift. So minus will appear here. Understand? So both magnitudes are same. Both the magnitudes are same, but there is a phase shift of 180 degrees between the two inputs. So we can say that Vs by 2 minus of Vs by 2. So what is this expression now? It will become Vs by 2 plus Vs by 2, right? So this is going to be Vs now. So the difference voltage is said to be Vs now here. Clear? Now the magnitude of the differential gain AD. So we need to find the magnitude of the differential gain. So what we said, the expression for gain here, voltage gain. So voltage gain is defined as V0 by Vs. Voltage gain is defined as V0 by Vs is equals to minus HFE into RC by 2 into RS plus HIE. Right? So what we said about Vs is nothing but the input voltage. So in the analysis, what is the input voltage for differential mode operation? See, the differential amplifier will operate in two modes that you need to remember. One is the differential mode, another one is the common mode. The differential amplifier circuit will operate in both the differential mode as well as the common mode as well as the differential mode. So don't confuse yourself how it will operate both simultaneously. Understand, this is a circuit that will exhibit the phenomena of differential mode as well as the common mode at times. That's what you need to remember. So whatever the output you are getting, the output is the combination of both of these. Understand, the output of the differential amplifier is the combination of both differential mode as well as the common mode. That is what you need to understand here. You cannot visualize or you cannot see how it is when it is not just like a train passing here. At 120 I have a train and 130 I have another train. No, not like that. The entire output of the differential amplifier consists of combination of both differential mode as well as the common mode gain values. Right? So in the differential mode, how will you set the differential mode here? Vd is equal to V1 minus V2. Under this mode, what is your input voltage? Vs. Right? Now what is the gain of this differential mode here? What is the gain of the differential mode? Gain means output voltage by input voltage. What is your output voltage? V0. V0 is the output voltage and input voltage is going to be the Vs. So this is Vs is nothing but the input of your differential mode, input of the differential amplifier under differential mode. So the same expression which we obtained in the previous expression, that is minus, of course minus will be there, so don't confuse HFE into RC by 2 into RS plus HAE. So whatever we consider here, this is for balanced output. So if you remember, differential amplifier itself can operate in 4 modes. So what are they? Single input, balanced output, dual input, that is nothing but balanced input, balanced output, balanced input, balanced output. What is by balanced input? Both inputs are available and both the circuits will give the output, right? This is what we consider. Similarly, for unbalanced output, for unbalanced means what? There is only one output. There is only one output. The other circuit output is grounded. Unbalanced means out of the two transistors, out of the 2 circuits, only one circuit will give the V0. The other circuit output terminals are grounded. So that's what you need to remember. The analysis is very same. So only thing is, so you must be very clear in terms of the balanced and unbalanced. Balanced means both the transistors will produce the output. There will be V01, that is VO1 as well as VO2. This is what the balanced output. Unbalanced means this VO2 is connected to the ground. That is the output terminal of the transistor. It can be the first transistor or the second transistor is grounded. This is nothing but unbalanced mode. Okay, don't confuse this one. So the analysis is very same. You need to consider the nature of your circuit, right? So this is what we have seen now. Now the expression for AD with balanced output. What will happen to the AD with the balanced output? So here you just see here. Here we have HFE into RC by 2 into RS plus HIE, and this, do remember this expression. And for balanced output, what will happen? Both the transistors will produce the output. So what we said, this is the gain for coming out from a transistor. It can be your first transistor or it can be the second transistor. So while suppressing the output terminals of the other transistor. So that is nothing but unbalanced mode of operation. Now if it is the balanced mode, what will happen? Both the transistors will contribute the output. And will deliver the gain. So we can say that same expression is going to become twice. So here if you observe here, the term 2 will appear here. That is 2 into. So previously this is, if you close this one 2. So this is the expression for unbalanced. For balanced means both the transistors will contribute some amount of gain. So it is going to become 2 into HFE into RC by 2 into RS plus HA. So the denominator and numerator 2 will go out, will cancel each other, and we left with HFE RC by RS plus HIE. So this is the differential gain of the differential amplifier. So this is the differential gain of the differential amplifier. And similarly, we need to determine the common mode gain. So I will tell you what is meant by common mode gain here. So what we said, the differential amplifier will operate in 2 modes. What are the differential mode as well as the common mode? So in the case of common mode differential amplifier, right? So there will be a common mode signal. So we said for differential mode we said VD. What is VD? VD is equal to V1 minus V2. For common mode operation, VC is equal to, it is the average of the 2 inputs. We can see it is V1 plus V2. We can say it is going to be the V1 plus V2 we are going to have, right? So this is to be considered. This is the signal to be considered for common mode operation of the differential amplifier. And now, what is your output voltage? If you consider both the transistors, that is, let us say A1 into V1 plus the output is going to be the A1 into V1 plus A2 into V2, right? So this is the output voltage of the differential amplifier under common mode gain, under common mode operation, right? So we also know that V0 under differential mode, it is going to be the VD, or it can be AD. In fact, it is not VD, AD. V0 is equal to AD into V1 minus V2. So we need to remember these expressions. These are some standard expressions, right? So if you consider both these two expressions, let us say this one has some equation number 1, and say this is this as equation number 2, right? By considering these two expressions, we can rearrange. Let us say this one as third equation. We can rearrange the third equation. So what we can say here, so V0 can be written as, let us determine the values for V1 and V2. So what is your V1 now from equations 1 and 2 here? So V1 will be your Vc plus 1 by 2 Vd, and V2 is equals to Vc minus 1 by 2 Vd. So these are the values or expressions for V1 as well as V2, right? So keeping these two things, we can slightly modify the expression for V0. So we have expressions for V1 as well as V2. Okay, so do remember what is the expression for the output voltage? V0 is equals to A1 into V1 plus A2 into V2, and we find the expression for V1. What is V1 here? V1 is equals to Vc plus 1 by 2 into Vd. By simplifying the expressions 1 and 2, we are getting these two. And V2 is equals to Vc minus 1 by 2 into Vd, right? So now we can rearrange this particular equation by substituting the values for V1 and V2. So what will happen here? V0 is equals to A1 will remain same, A1 into, so what is Vc? What is V1 now? Vc plus 1 by 2 into Vd plus A2 will remain same, that is A2 into, what is V2 now? Vc minus 1 by 2 into Vd. So this is what we are getting for V0 now. So if you simplify this expression, because there are some common terms, if you observe, there are some common terms. So what we can get here, 1 by 2 into, it will be your A1 minus A2 into Vd plus A1 minus A2 into Vc, right? So this I can write it as AD into Vd plus AC into Vc, we can write it. So where AD is nothing but the gain of the amplifier under differential mode. The gain of the amplifier under differential mode, and AC is nothing but the gain of the amplifier under common mode. The gain of the amplifier under common mode here, right? So keep this expression in mind, and we will continue the discussion in the other session. Okay. So up to this, you can hold the expression for V0. So now we are able to express V0 as the combination of both the differential gain as well as common mode gain. So we are going to define another term, that is common mode rejection ratio. So this is very, very important for differential amplifier. So we will continue the discussion in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.